Hello and welcome to this technical walkthrough. I'm Matt Landers, co-founder and CEO of Covalence, and I've been working on this C# course, and I realized that some of our students and alumni may not really know a whole lot about how computers store numbers, specifically when we're talking about floating points. So in JavaScript, you don't really talk a whole lot about how the numbers are stored or floating points because that's kind of handled behind the scenes for you. But when you're in other languages, you got to be really careful based on what type of data type you use to store these numbers, because you can run into some serious issues, especially if you're going to be working on a banking application or something like that. So let's start out first and talk about what is a floating point. So whenever we're talking about really large numbers in science, we usually don't type out the entire number. For instance, Avogadro's number is 6022, some huge number with 23 zeros, right? It's like, I think it's 6022914, whatever. It keeps going on and on. And we wouldn't want to talk about that and write it down everywhere with 23 zeros. That's crazy, right? So what do we type instead? We type 6.022 times 10 to the 23rd. So in C# E23, that means that's the exponent. So we're doing times 10 to the 23rd here. That's how we do the scientific notation. So this allows us to express this really large number in a condensed way. And we need to be able to do this whenever we're talking about large numbers, or we would use up a lot of space on disk. I mean, one really large number could take up, depending on the size of the number, a meg or more, just for store that one number. But when we condense it down to this size, we can get a 32-bit number that stores pretty large values. But what's happening here? So we don't really get the exact number here. This is what we're used to using in calculations using Avogadro's number, but we're not getting the absolute exact value because we're losing everything after the 0.022. Now, because the number is so incredibly huge, it's not really that big a deal for our calculations because we're not really off that much percentage-wise. It's very, very tiny, right? But imagine that we're doing something with money. Then this becomes a really big deal whenever we lose accuracy, because cents matter in this case, right? So let's talk about what's actually happening, how it's stored, and what it looks like. So why do we have to do this? Well, what happens is that this period gets moved all the way to the front of the value, at least in C#, and how it's stored. And let me show you how that works. So if we have this huge number, and in a floating point in C# is up to 7 digits. So let's say that we do 500,000.01. Now, what's happening here is that we have more than 7 digits. So we have 6 digits and before the decimal place, and then 2 after. So we have 8 possible digits. Now what the computer is going to do is move this decimal place over and then decide where that should be stored. Now why is it doing this? Because if we think about how a computer stores data, it just stores it in bits. So ones and zeros, bytes and bits. So it's like this. This is what a number might look like on the disk, right? A 32-bit number is going to have 32 ones and zero possible combinations. So it's still larger than this, but you get the idea. But if I wanted to know where the decimal place was in this number and it was random, there's no way for me to know when I'm taking this off the disk and turning this into an actual number. Everything's just a 1 and 0. I could say that a 0 is a decimal place, right? Let's say that represents a decimal. I wouldn't know which 0 was the actual decimal because we can only store 2 possible values in each bit. So what we do is we say, all right, well, we're going to move this decimal place up to the front, and then we're going to determine how many exponents we need, okay? So we get all of the significant digits to the left to not be there anymore on the decimal place. So it'll go something like this, right? And then it's going to store, based on the size that we have available for the storage. So in float here is 32 bits. It's going to at some point store in a specific place how many decimal places in either direction to go. So And that's just in a specific place. So we always know that it's there. So when we're storing it as ones and zeros, we can find it. Now, that's a lot of complication to get down to the point, and I'm trying to make it as understandable as possible. But at the end of the day, there's a practical reason that you need to know this, and that is that accuracy is definitely lost. So if you're going to do a banking application, then you're not going to want to use a float. And let's look at why. So let's look at this example here. So right now I'm just doing one F here in C# just denotes that this is a float. So I have to put that there. Otherwise, it's not going to like me very much eventually. So I put that F there just to say that this is a float. All right. And then whenever I run this, this is going to do what we expect. So it's 1 minus 0.01. And what I'm outputting here is what is the value of F1, what's the value of F2, and then are they equal or not? They're obviously not equal, 1 and 0.99, right? And the equality thing is, here is important because you may be doing things in your applications where you're checking the equality of two numbers, and you may not be getting the result that you expect. So let's look. So now this is only 3 decimal places because we do 1 minus 0.01. We end up with, well, it's actually 2 decimal or 2 number places, 0.99. So now let's just make this a little bit bigger. Let's say that we do 1, 2, 3, 4, 5, 6, 7, which is the size of the accuracy that we get with a float, minus 0.01. What's going to happen here? So now look, it thinks that these two numbers are the same. Why is that? So what we did was we said 1, 2, 3, 4, 5, 6, 7. That's the level of accuracy that we get with floats in C#. And then we subtracted 0.01. But that 0.01 comes after 7, after the 7 here, which is already 7 digits. So it just doesn't care about it anymore. It can't store that number. It gets rounded off. So it looked something like, it should have looked like this, right? 1, 2, 3, 4, 5, 6, 0.99. But we didn't get that, or should have been 699. Yeah, so we get 2. We didn't get this because these two numbers can't be saved, right? So when we did the subtraction, it didn't even take that into account because it couldn't. And we ended up with the same number that we started with, and it thinks that these two numbers are true. So I just want to show you that again because this is really important. This could be a big deal in your applications. So there we go. They look exactly the same. Now, let's say that we're dealing with money and we had $100,000, which, if you're dealing with a bank, this isn't exactly a huge number, and we want to subtract 9 cents from that. What is going to happen here? So we got that actually worked because the number wasn't big enough. But if I change this to 5, and the reason that didn't work is just the way that the binary is stored, but this is going to push us over the limit here. 500,000, 0.01 minus 0.09 should be, this is harder for us to tell what's going on, so I'm going to do 0.2. So this would mean that it should be 49999.9999999. And now look, we have them both saying that they're equal to 500,000, yet the equality is still false, which seems bizarre. Let me do this a different way that I had it in the example here. So this should be 500,000.24. This will be a lot easier for us to see. Sorry about that. And there we go. It thinks that these two numbers are true. Now, we're not talking about a huge number here that you may not run into whenever you're working in a banking application. This would be pretty easy to run into. And we're subtracting a cent, and this matters in this point. We're losing money at this point. It doesn't, we actually lost 5 cents there. I don't know if you noticed that, but when I run this, because this 5 can't be stored, it looks like it's 20 cents now instead of the 2.5. Even it got lost, you can tell here. And if we were to add another number here, so let's say that I had 1 here and then Now we're going to lose even more fidelity because we're chopping off all of those other numbers. So this would not be good to be using in this case, because this is how it's actually stored. It's just 5.55 times 10 to the 7. And now we're losing this $1.25. We still have the 5.55, but you can see where these calculations could go really wrong at some point. So you got to be really careful whenever using this. Now in C#, we have a 7-digit accuracy, no matter where the decimal place is. That is really key. I think that sometimes that might get lost in the translation. Now if we do a decimal or a double, we don't have this problem on this particular number because it goes between 15 and 16 digits on its accuracy. So if I change this, we will end up with the expected result that we weren't getting before. See how this is no longer showing us the scientific notation anymore. We don't have that E in the number. But if we did make this number really big, we would run into that issue again. And let's just do it just to show it. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8. Then we have the 2, 5, which is 9, 10. So I need 7 more to be safe. 1, 2, 3, 4, 5, 6, 7. And now we should run into the same issue that we were having before where these two numbers are true. And there we go. So a double will give you a little bit more room to not have this issue, but it's still going to have the problem. Now, if you want to be sure this doesn't happen in something like C#, we can use the decimal data type. And it has an accuracy of, this number is too big for this, for a decimal. We have to come down, I believe, just 2 more. Oh, well, we got to change it to money as well. And it has a pretty large accuracy, but you can always know that a decimal is actually going to give you what you think. So if you're going to use money in C#, you want to use a decimal. And you'll see this in other languages as well. Like in a database, you'll see it in MySQL, you'll see it in SQL Server that you can use a decimal. And that's usually used for money rather than a float. Now there's another way to get around this without even having to worry about decimals. And we can just use integers and longs to do this, and we store everything in cents. So if we store everything in cents, then we don't have to worry about a decimal place. We just always on the front end divide by 100 to show the user what it would look like if it were in dollars and cents. And that's really the safest way to go about this if you don't know how your language is working, is just never store decimal places. Now, and use an integer too. Don't use a float there because you're still going to lose the fidelity because it's going to chop off even whole numbers at that point. You got to make sure that you use integers that are for sure going to be what you think they are. And you'll run into this more often than you think because calculations will overflow that, that fidelity, right? So if I do 1 divided by 3, that's a repeating number. It's 0.3333333333 easy. Like forever. So that is another way that you can run into this issue where you have way more decimal places or more numbers there than you think that you do because you do some type of calculation where you have an infinitely long number. And this basically is all that I really wanted to talk about in this video and get the point across that if you're using floats, you're using doubles, you can't be sure of the accuracy of the calculations that you're doing. They're meant for really large numbers. You see this in scientific calculations. So if you think large scale, how many feet is it from here to Mars? If we're off a little bit, not that big of a deal. If we're doing tiny quantum physics calculations where they're really, really tiny, then if you're off just a little bit, it's not that big of a deal. But it is important that we understand how these are being stored, especially if we expect to get the completely accurate result, and if we're going to compare two numbers together, that's going to have an impact on whether the equality comes out correctly or not. So this is how floats work. Hopefully you learned a little bit from that. I know that it was a little bit complicated, but thanks for sticking with me, and be careful out there when you're floating.